Does anybody have any questions about what we've covered so far?
I have a quick question.
Sure.
Since I'm kind of unfamiliar with what raster data sets are, could you explain them just a little bit more in detail?
I can explain them in extensive detail, and we're going to get into them a little bit deeper as we go through here. But in a nutshell, a raster data set is any data set that you can visualize in a, I think of the right word here, as more of an area than a discrete object. And it's different from an area object like this one in that it's a continuous representation of the data within that area. So if we cover our whole area with this raster data set, we include a lot of information with that within that area versus just this area boundary that tells us essentially the boundary and maybe what's in it. So raster data sets can be things like images, they can be things like 3D surfaces. That's not exactly a raster, sorry. They can be things like 2D representations of 3D surfaces, elevation data sets. Sometimes you'll see satellite imagery as far about vegetation coverage represented in a raster data set, or a satellite heat map representing temperature response from the Earth as a raster data set. So it's a continuous data set over an area and often over very large areas.
Can you combine data sets, like combining a raster and a vector data set to like get a better idea of a area or map you're looking at?
Yeah, absolutely. And that gets back to the multiple thematic layer that we talked about. So this elevation map right here is a raster data set showing your elevation in, what was the word that we used to see? If this were color, it would be a color rendered shaded elevation surface. Since it's not in color, it's a shaded elevation surface. And then similarly with this aerial image right here, this is a raster data. I've also seen things like soils and wetland mapping represented as a raster data set, although sometimes they're more useful as vectors.
Thank you.
Mm-hmm. So diving in a little bit more into rasters. They are typically, although not always, developed as a square grid system. So you have, an X coordinate and a Y coordinate if you're talking about a Cartesian system, and you describe each of those cells individually. So that can be things that are discrete data points, like this one, where you're representing different types of information, and it ends at that boundary, and there's not a gradient of information between A and R. Or you can represent things that are more of a continuous data set. Anything else on this slide that I'm, yeah, and it's essentially the same thing as representing a vector data set, in that you have a position that describes the location of the information, and then you have an attribute that you're showing. With a vector, you're showing that attribute on its face instead of in an attribute table that you then have to apply a style to an object like we were doing last week. So as I mentioned, there's two different types of raster data models. There's discrete raster data models where you're essentially binning your data. If you've ever done any type of computer modeling, a bin represents a area or a volume of a specific dimension, and the attribute that you're trying to quantify is assigned to that bin. So each of these bins has an attribute assigned, versus a continuous data set, like something like an elevation, or maybe you're representing a gradient of temperature. Those things are certainly binned. There's a difference between, even if you had 670 and 671 side by side, there's a strong, there's a dividing line between that, but it's a little bit more of a continuum. And and you're representing a slightly different type of data with that information. So here you have a difference between 744 and 745, but it's a little bit different in the concept than the difference between U and A. And what that means, so you're taking your data and you're binning it and you're assigning an attribute to it. And that means that somebody had to make an interpretation at some point, whether it was in defining our numbering system whenever we did that, or assigning some sort of qualifier to an attribute. And so our exercise today is for you guys to do that. So what I want you to do is identify each of the squares within this map as land or water. So you should have in Pear Deck now the ability to either draw, or you can use, I think, the little text box and put a L or a W in each of these boxes. And let's all start in this upper left corner and work out from there, because I found it a little bit slow, so we might not get through the entire grid. But just to kind of get a sense of what everybody is interpreting this as. So is this box number 1 land or water? And I'm going to give you just a couple of minutes to do that, because I think it's interesting to see the ways in which people might interpret things differently. And if you're having trouble with the drawing tool, you can try out the little text box tool too. Okay. So you guys are kind of fascinating in the different ways that you chose to interpret my instructions. Why just have 2 choices? There's obviously an intermediate category, and that is a totally valid way to interpret your raster data into a discrete system. Add a 3rd category. Why use L and W? This is a really clear visual representation. Similarly, this one. I was really hoping it was going to let me overlay your responses, because I think what's really interesting as well is the differences in interpretation. So here we have somebody who, it looks like anytime there was water within the feature, called it water. Here we have someone who, it looks like, probably said, okay, this is a certain percentage water, we'll call that water, but I'm not going to call this one water, even though maybe you could interpret that as a water body, because it doesn't really fit my criteria of what I interpret as water. Here's a really good example right here. Here we have 2 water bodies. I'm going to interpret that as 2 water bodies. But I'm going to choose to not represent the fact that there is water within these 2 grids. And that's, again, a totally valid data representation depending on what you're trying to get at. I'm not sure what the little Cookie Monster dots are about. That's an interesting feature. So again, I wish I could overlay these, because I think it would be really interesting to see the differences in how people chose to interpret things. And they're all just different ways of approaching the same problem. And so they're probably all equally valid, depending on what you're getting at. So we've actually defined some of these different systems. Get back, there we go. Into some systematic ways. So we have winner takes all, which is essentially a way of saying the majority of this area is clearly water. So I'm going to call this water. This one, I would say probably also a majority water, or that might be close. I'm going to call that water, but this one is a majority of land. So I'm going to call that land. So winner takes all. We're just going to go on proportions and use that as our defining characteristic. There's one that's really important to raster data sets called cell center. And that's saying at the center of this cell, stop clicking, it is land. At the center of this cell, looks like I'm probably in that water body, so that's water. So cell center. There's also another approach which is cell reference point. For Cartesian systems, you typically have an origin in the lower left corner. So you're going to define your raster attribute based on the lower left corner in many cases. And then there's what's called preference for water in this system. And that becomes really important in management systems. So I do wetland mapping as part of my work. If I am trying to map wetlands at a certain scale, say I'm interested in any wetland that's over 10 feet square. If there is a wetland over 10 feet square within that raster grid, I'm going to flag it as a wetland, because the consequences of not recognizing the fact that there's a wetland there have serious ramifications for my client. So that becomes a system where you're balancing the risks of not representing potential data against the risks of overrepresenting your potential data. If you were trying to, I don't want to get too political, but if you were trying to represent the political orientations of an area, so you're trying to represent the ways in which people vote in an area, you're going to be try to focus a little bit more on the majority than trying to make sure that your own personal preference is represented. Or at least, hopefully, that's how you would approach your mapping. We're not going to get into gerrymandering with GIS systems, but it is a thing. So that's the decision-making process of how you're defining your raster. Very little of that is done in the way that we've just done it, where you're making a decision grid by grid, because that would really defeat the purpose of a raster, which is to capture large amounts of data in a easily represented data set. We're talking about processing huge amounts of data here. So most of those decisions are made by computers, but you still have to set up your computer system to make the decisions in the way that you want it to. So then the next aspect, sorry, does anybody have any questions on that before I move on? Okay. The next key aspect of rasters is the resolution of that raster. There is a big trade-off in how much space your data takes when you're representing it for your, the number of grids that you make. For every additional grid split you do, you end up with 4 more pieces of data. So your data size can quickly grow depending on how small your resolution is. But there's also some decisions to be made of, if I was just going to come out and make an identical model of the Earth, I would be building a new planet, and that's not what I'm trying to achieve here. I'm trying to represent our data in some way. So I'm going to grid it at a resolution that meets my needs but doesn't mask my needs, and that can be a fine line to walk sometimes. And it can really vary by region. If you're trying to capture water bodies in Arizona, you can probably do that at a much grosser or less fine resolution than, say, Minnesota, where you have water everywhere you turn around. So there's decisions to be made as far as resolution as well. So this is where we get into the eternal battle of trying to remember what it means when we have a fine resolution. So I didn't put a Pear Deck response in here, but I want you to think about this question. What does a high resolution mean in terms of the size of your grid cells? And feel free to throw something in chat or pipe up.
A fine resolution would have lots of cells.
Lots of smaller cells, because they have to be smaller in order to fit them, right? So does that allow you a lower, higher precision in your data?
Higher.
Now you're going to have a lot less generalization in your decisions. You'll have to make fewer decisions because it's going to be more often really clear what that cell should represent. And then there's the data storage trade-off. So what happens if we have a really fine resolution, small grid cell, high precision data set? What does it cost us?
Greater.
Yeah, we have a much greater data storage cost to that data set. So here's where we get into the fact that we've now represented this data as squares. And I find it interesting to consider the fact that you don't have to represent a raster data set as squares. As you saw in the tin data set, tins more often tend to be triangular because that's what they're designed to do. You're looking for 3 points. Squares are square. There's a new trend in GIS that I find really interesting to use hexagons. And that's used heavily in data sets to map local variation on a regional scale. You tend to have less masking, at least from our human perception and our human interpretation of what we visualize in a hexagon is different than what we visualize in a square, and I find that really interesting. If you're at all familiar with some of the data sets, that Axiom Data, they're a local company that's done a lot of the hexagonal mapping of our state. It's an interesting, newer way to represent data. We're not going to have any hexagonal data sets to play with, but something to consider is that you're not always trapped to a square. So what does a square mean? If you split that square into half the size in resolution speak, so if I go from 100-meter resolution to a 50-meter resolution, what does that do to my storage space? And we've gotten a lot of answers back. You now use 4 times as much because it's a square. Or if you split it again, you're 64 times as much data. So every time you decide to increment it down, and you know, sometimes I'm sitting there and I'm making the decision, all right, the engineers asked me to export this data set into an elevation model, and they're going to throw it in ArcGIS, and if it blows up ArcGIS, they're going to blame me. So where do I strike that balance? Do I do a 100-meter grid and they think I have a lame data set and I haven't really captured the area very well, or do I give them 25-meter resolution and maybe they're running this on an old computer and it totally blows up their system and they blame me for that too? I'm going to figure out what their data needs are, what they're trying to represent, how they're going to use it, and I'm going to make my resolution decision based on that. And all of that is different now because we're no longer on connected servers. We're in a cloud. Just makes everything more interesting. So, in a nutshell, what all of that means is we are taking real-world data and representing it as digital object models. And I've maybe kicked some dead horses there, but I hope that it has helped really conceptualize to you the decision-making process that goes behind all of this GIS data. It's given to you in the form that it's given to you, or you develop it in a certain form to meet specific goals. And it's important to keep those goals in mind while you're developing it or using it, because it's going to affect the outcome of what you create and what you can represent.